Julio concert. Of course.
Do you guys play instruments?
Yeah, I've played piano for about 12 years.
Oh, oh wow. Oh wow, cool.
I stopped playing when I was 18. I'm trying to pick it up again during the summer after I
Oh, please
graduate,
do.
probably.
Yay!
I have a keyboard.
I'm trying to pick up piano again too.
Oh, nice.
Oh, nice.
Yeah, I used to play piano when I was a kid too. But then I played piano from I think second till eighth grade, and I quit because I saw piano really pointless at first. But then many years later, coming into my first year of college, when I started listening, to Studio Ghibli piano music sets, that's when I realized, oh, this is why my mom wanted me to learn to play the piano. So
yeah.
that's that, because it got me thoughts of saying, man, I wish I could play as good as this. Now I understand why my mom wanted me to play the piano.
For real. Like Studio Ghibli.
Yeah. Ghibli,
that composer,
Ghibli, who cares?
I don't know. But the way he's able to capture a vibe is amazing.
I know.
The one song from Spirited Away, the summer one.
The One Summer Day?
Yeah, the first chord immediately, you're taken away. First chord, it's
yeah.
If I was gonna learn piano, that would be the first song I learned.
Oh yeah. I mean, the Studio Ghibli series, no doubt, those are really good movie series.
100%.
Yeah.
Okay.
All right.
I love this conversation, but I think we should probably start. Although this meeting will be a slightly shorter one. I think I'm planning out it to being about 30 minutes. So we'll definitely have time for questions and Ghibli piano talks after, if you guys want to talk about that. I love music and theory and piano. So if we want to talk about that after, I am not going to say no.
Yay.
Back to brain stuff, because that's pretty awesome.
Yeah.
So
because the brain is a complex and beautiful thing.
It really is. And so this topic is going to be less technical. We're going to take a step back from all the ML and the code and stuff, and we're pretty much going to just be talking about neuroscience stuff, psychology, just different brain waves and that aspect. So we'll be talking about different brain signals that are used in BCI projects and basically, why we use them and how it works in the first place. If Jillian wants to introduce the club.
Oh yeah. Before we get started with that fun stuff, just a little bit about NeuroTech at UCSD. We are affiliated with the NeuroTech X International Organization, which is a really large organization actually that connects people with neurotech passions from all around the world, companies, research labs, students together. And so we are one of their official chapters. In the NeuroTech X program, there is an annual student NeuroTech X competition, and this year would have been our first year to do that, but unfortunately, due to the current circumstances, we were not able to do that, and so we're planning to have a great year next year to be able to compete in this competition, where you get to build a full engineering project for some sort of BCI device. So you get to come up with your own engineering problem and also execute the entire engineering aspect of it to create something that is useful. Our faculty advisor is Professor Vikash Gilja. He's part of the TNL research group here at UCSD, and he is also an ECE professor. He's also worked at the Neuralink company for about a year or so. So he's a great resource for anyone trying to get into this field. We also have connections with Wearable Sensing, a local San Diego-based hardware company. And we're also trying to explore more companies around the area as well to gain more connections for our members who are interested in working in this field. And also we have multiple headsets for project groups next year. So we have OpenBCI Ganglion that the club has acquired, and also a Wearable Sensing DSi-7. So these two headsets will definitely allow us to create some cool stuff for next year. And especially the Wearable Sensing DSi-7, that one is a research grade Bluetooth EEG headset. So we're definitely looking forward to you being able to use that. Cool. So without further ado, I'll hand it back to Kevin and Henry.
Okay, here's a quick poll. As a participant, put a check mark up if you have a solid foundation of things about the brain, if you're like a cog-sci major, if taking classes before. Put a hand up if you have basic background knowledge but are not very comfortable in like explaining all this stuff yourself, and put an X if you haven't taken like anything neuroscience related and you don't know much about anything. Also, just as a joke question, have you used a brain before and why? I certainly have not used one yet this quarter, but hopefully that'll change during finals week. Okay, so those with the check marks, which is some of you guys, this is going to probably be mostly review. You might learn a little bit about why we use certain recording techniques or a little bit about EEG headsets, but most of this lecture will be review. Although this lecture is going to be more casual and relaxed, and as I said, only 25-30 minutes, so it shouldn't be too bad. Those with X's or hands, I think it's X's besides the check marks. Yeah, there'll be a lot of stuff to take in, but our slides will be online, and then you can always ask us questions as well. And I'll try to slow down if I'm going too fast, or you can always tell me to. Okay, here's the presentation outline. We're going to review the brain, and we're going to go over the different parts of the brain and what each part is thought to do. All the stuff that we're going to go over is what people think is true, but the brain is really hard to research, and it's kind of an unknown space, which means the main way we understand why part of the brain corresponds to a part of your senses or whatever it corresponds to is because due to like brain lesions and some very unethical studies. So yeah, don't think everything as a guarantee, but this is basically just the guidelines that modern day cog-sci and psychology follow nowadays. And then we're going to go over the types of brain waves, which ones we record and why and where they're located in the brain. Then we're going to go over different brain recording techniques, and particularly EEG and MEG, because those are the most common ones for BCI projects. And then after that, we'll talk about different ways we either give stimuli to patients or why like different ways we record the brains through exogenous and endogenous methods, and we'll go in more detail what that means. Okay, so this is a basic review of the brain. You would learn this in any Psych 101-esque class. So the brain is broken up into 4 main lobes. The frontal lobe is for decision making. It's basically where a lot of your personality is. And they figured this out because of a patient who lost part of their frontal lobe in an accident. Used to be a really nice guy, and then he all of a sudden became really angry and frustrated with the world, and no one liked him anymore. And so, you know, psychologists thought, oh, probably your frontal lobe is important for your emotional control and your personality. It also controls the Broca's area, which is in charge of language and primarily speaking, so the physical aspects of language. And then the most important for BCI projects is that your frontal lobe contains the motor cortex, which is the back ridge in between the red and the yellow section in that picture. And the motor cortex is really special because it's broken down based off of your body. And different parts of the motor cortex is correlated to different parts of your body. The ones that have more senses and feelings or like easier to move have a larger portion of the motor cortex. So for instance, your hands have a lot. Yes, Phineas Gage. Your hands have a large section of the brain corresponded to the motor cortex, and because your hands have very strong ability to move independently, so has your tongue and other parts like that. Whereas something like your abs, you can't really flex them or control them very well, so it's a very minor part. And that's actually pretty important for BCI projects. And then the next lobe we're going to go over is the parietal lobe, which is the yellow one right behind the frontal lobe. Parietal lobe is known for spatial reasoning and spatial awareness. It's also where S1 or the somatosensory cortex is located. The somatosensory cortex is basically the same as the M1 motor cortex in terms of the layout. The somatary is for feeling and the senses. So it's like, once again, your hands take up a large portion of your somatosensory cortex because your hands have very strong feeling. That's why when you touch something with your hands that's hot, it hurts a lot more than if you touch it with your arm. It takes longer to process and it's not as severe. Next, we'll go to the occipital lobe, which is in the back of your brain. If you feel where that little part of your skull back there is, that like protrudes a bit, that's around where your occipital lobe is located. This is where all your visual information goes. There's also other things that happen on the occipital lobe, of course, but the most important thing for BCI projects is the visual information. So we'll be focusing on V1 a lot. when we do projects, just because we use visual stimuli quite often in our BCI projects. And then the other stimuli we use very often is auditory stimuli, and that's why the temporal lobe is really important. Temporal lobe is located around your ears, and that's where all auditory information gets processed after it goes through your ears. Once again, this is important to focus on due to any project that takes audio stimuli. And then the last two parts on the chart on the right are your cerebellum and spinal cord. These aren't really commonly recorded, but just for your guys' background knowledge's sake, the cerebellum is in charge of a lot of muscle memory and balance. When you want to play the piano, ride the bike, things like that, it's all through your cerebellum. And the cerebellum is also the first thing to get impacted by alcohol, which is why when you drink too much, it's hard for you to stand up straight. And then spinal cord is where all your information from the rest of your body goes up to your brain. Is also in charge of reflexes and other life-saving things. So yeah, take good care of your spinal cord. Okay, and I'm going to go into some of the more complex brainwaves, and then we'll go into more general stuff with Henry in the next slide. But I wanted to just, as a kind of like a quick aside, talk about these really cool things called mu rhythms, because it's a brainwave that's not very commonly taught, but it's something that's actually used quite a bit with research that regards EEGs, and it's very common, and it's actually kind of a new thing that came out of research in the 93, I think, 1993. Anyways, mu rhythms are kind of brainwave that appear in your motor cortex. And what happens is these brainwaves get inhibited when you are thinking about doing an action very strongly. And the actions are something like, you know, picking up an object, eating an object, swimming, jumping, ing words, action words. And what's so cool about mu rhythms is one, they can be recorded and you could use it as a trigger. Like for instance, when someone starts inhibiting their mu rhythms because of thinking about doing an action, you could in theory record that and see that and use that as kind of like a classification technique in your BCI project. But in addition, there's been a lot of cool research that I wanted to talk about a little bit regarding mu rhythms, and it's a system called the mirror neuron system. And what mirror neurons are is there's these neurons in the Broca's area, which is in your frontal lobe. And mirror neurons will activate when you see someone else doing an action that you've done before. So for instance, if you watch another person pick up an apple and eat it, or watch a person swim, or watch a person jump up and down, then your parts of your brain that would be required to do those actions will start activating as well. And the reason why the research in this area is so cool is, one, we hypothesize that the reason why we have these neurons in the first place is to help us as social creatures imitate our peers and learn how to act based off of watching, kind of like a baby watching its mother. And then two, we wanted to see what would happen if the mirror's neuron system was not as functional. And there's been some research, and there's suggestions that show that people who are on the autism spectrum, who have ASD, they actually have a malfunctioning or not as good functioning mirror neuron system, and therefore it's harder for them to understand and imitate other people around them, and it causes them harder for them to understand why someone's doing a given action. So there's actually been some studies where they've done neurofeedback with BCI or with EEG headsets and video games to try to help people on the spectrum train their mirror neurons and train their mu rhythms to inhibit correctly when they're watching someone else do an action. And they showed some signs of being able to understand emotions better. So it's hard to say whether it's actually a cure or not. A cure is not a correct word, but whether it would help people who are on the spectrum. But it's certainly looked into as a way to maybe help them socialize better. And another one I want to talk about is VEPs, which are visually evoked potentials. And basically, that's just brainwaves that are shown through the occipital lobe. All the electrodes that we'll talk about later in the occipital lobe will trigger when you look at things, because all your visual information is processed in the occipital lobe in V1. So those are really important, and we'll bring it up a couple more times. So I just wanted to bring it up briefly right now.
Cool. So now I'm going to talk about brain frequencies. They're sorted by frequency band. So starting from the bottom, you have delta waves, that's 0 to 4 hertz. And they're generally associated with deep sleep. And the association here is just that when you're in deep sleep, the delta waves show up more than they would normally at other times. So it's like they're showing up more relative to themselves rather than like more relative to the other waves. Theta is 4 to 8 hertz, and that's like light sleep and drowsiness. Alpha is 8 to 12 hertz. That is when you're in a relaxed state, or if you like close your eyes, you can see more alpha waves. Beta is 12 to 40 hertz. That's when you're like alert and conscious. And gamma is the highest at 40 to 100, and that's focused, intense thought. So generally, your brainwaves have like a higher frequency. It correlates with how, I guess, intentionally you're focusing. So let's talk about some brain recording techniques. So we have EEG headsets. These measure the electrical activity, and they're the best for our use case because they're non-invasive and they're portable. So that makes them easy to use because they're portable and you don't have to open somebody's head to get in. So it's relatively safe. They have a good temporal resolution at 0.05 seconds, and they have a okay spatial resolution, but that's fine because the spatial resolution doesn't really matter as much as the temporal resolution. And they directly measure electrical signals in your brain through your head. So, somewhat indirect, but directly measuring that. MEG is the same concept, but instead of measuring the electrical signals, you're measuring the magnetic fields. And has the same temporal resolution, slightly better spatial resolution, but the MEGs are like gigantic machines, so you can't move them around. They're not portable. You need to use them to measure certain neurons because of the way they're oriented in your brain. But we don't have to. We won't be using them. ECOG and intracortical neuron recording are both invasive methods that will get you really good temporal resolution and really good spatial resolution because you're inside their head. And if you're intracortical neuron recording, you could be in a single cell or on multiple cell scale. So they're in your head, so they're portable kind of in that sense, but they're invasive, so we're not going to be using them. And then the last kind of recording method, I guess, is metabolic. So these fMRI and NIRS both use they both measure the blood flow in the brain and correlate that to the activity. So the temporal resolution is really not very good. It's around 1 second because you're measuring the blood flow after you've thought about something. But the spatial resolution is really good. So fMRI is non-invasive, but you have the spatial resolution on the scale of ECOG. So that's good. They're not fMRIs are not portable. Obviously, they're the giant spinning magnet machines. NIRS is near infrared spectroscopy, and these are non-invasive and portable, but the temporal resolution isn't very good, so we don't really use those. So kind of to bring it back to the beginning, we use EEGs because they're the most portable, safest, and best temporal resolution because it matters more than spatial resolution.
So I'm going to explain a little background information about how neurons work, and just so you guys can get a kind of feel of why these EEG headsets work. So there's millions of neurons in your head, and these neurons are incredibly long, and they connect to a lot of other neurons. And these neurons have to talk to each other, and the way they talk to each other is through chemical communication. They send tons of chemicals through their bodies, and those bodies reach from one end to another of a neuron. And then once it reaches the end, they communicate to all the neurons that's connected to that neuron. Then, hey, you need to send another signal. But luckily, these chemicals that they send are ionized, which means they have a charge. And so when these chemicals flow, you create a current. And this current is what we're trying to record. In fact, it's when one neuron talks to another at the end, that giant influx of a current is usually the one that's large enough to be recorded by one of our EEG headsets by creating an electric field. So if we go to the next slide, you can see that in a little more detail. So if you look at that picture at the bottom right, you see that arrow. And if you imagine that arrow being a neuron, and that neuron is firing a current in that direction because it's signaling to other neurons in that direction, then the electric field will be pointing in the same direction as that arrow. And the cool thing about, the problem with that is that means the electric field is going to be kind of parallel to the skull. So if you have a recording electrode on your skull, you won't be able to read that electrical field very well. So when you have a EEG electrode on someone's skull, The neurons that you can read the signal the most from are the ones that are perpendicular to that electrode, because the electrical field will be going in the same direction as the coding electrode. And then basically the reason why I wanted to showcase this is it basically describes the main difference between an EEG and an MEG in terms of what information you get. Since the MEG works in a very similar way, but it reads magnetic fields, if you took any E&M physics class or in general, you'll remember that when you have a current, you have a magnetic field in a 90-degree angle. So you see those rings that are near that yellow arrow in that blue picture again. Those rings represent a flowing magnetic flux due to the current. Now this magnetic field will be picked up from an MEG. So the MEG is better at recording neurons that are going the same direction, parallel to the electrode, whereas the EEG is better at recording neurons going perpendicular. Since MEGs are incredibly expensive and usually hard to move around though, we do use EEGs, even though we're not getting a perfect recording of every single neuron in that area where we have an electrode. But this just gives you a good understanding on how your brain actually creates electrical fields in the first place. There's not like a spark or anything weird in your brain. It's literally just positive chemicals flowing. It's mostly sodium and potassium and calcium just flowing through your cells, and that creates the electrical field.
Cool. So I'm going to talk about the standard EEG electrode placement system. It's called the 10-20 system. It's standardized internationally. The 10 and 20 are for percent distances around your head, either left, right, or front, back. And the names of the electrode positions are odd on, the numbers are odd on the left side and even on the right side, and Z for the center line from the front to the back, and the F is for frontal lobe, C is for center.
I think C just stands for center.
Yeah. P is for parietal, T is for temporal, and O is for occipital. Yeah. And then we're going to talk about BCI classification techniques. So you have exogenous and endogenous BCIs. So exogenous means you're using an outside stimulus, and then you're recording the brain signal that is reflected when you by the person interpreting that outside stimulus. And then endogenous is when you don't apply any outside stimulus to the participant. You just measure the signals coming out of their brain. The advantages for exogenous BCIs is that they don't really require any training, and you can set them up fast. The disadvantage is that the person who's using the BCI has to pay attention to the stimulus the entire time, pretty intently, and that can make them tired. Endogenous BCIs don't require any outside stimulus, like I said, but you need to train them for each individual, and training can be very difficult and can vary widely in across individuals in how well they can use the system. We'll go over these SSV, P300, SCPs, and sensory motor rhythms on the next slide. So VP is visually evoked potential. We talked about that in the beginning. And that SSVP is for steady state. So if you're looking at, let's say you have a stimulus flashing at a certain frequency, the SSVP signal, you'll see it match that frequency, and then you can determine, if you have multiple stimuli at different frequencies, you can determine which one the person is looking at. SCP is slow cortical, but let's talk about P300 first, because it's also exogenous. P300 is when somebody expects to see a stimulus, they'll have a different response than if there's a stimulus that they weren't expecting to see. And the 300 is for 300 milliseconds, because that's when that peak happens, is 300 milliseconds after you send the stimulus. SCP is slow cortical potentials. These are usually like less than 1 hertz, so super low frequency. And how you usually train it is you have somebody look at like a visual representation of the SCP, and then try and get them to be able to control it. And then if they can get to the point of controlling it, then they might be able to slowly control something, like move something like up and down in like a game or something like that. sensory motor rhythms are like motor imagery. So if you think about like moving your arms or your legs, then that when you think about doing it, it's reflected in your brain, and then you can use those to modulate stuff.
I'm going to go in slightly more detail about VEP since it's one of the more common ones. So VEPs are usually broken down in 3 different ways of getting your V1 to activate. One, T, F, and C stands for time, frequency, and coding. So for time VEP, or yeah, time VEP, basically, let's say, I'm just gonna use the example of a speller because that's a really hot topic right now, trying to build a type with your brain. So let's say you have 26 letters on the screen. Each of the letters flash at a different time. So whichever letter you're staring at will flash at a certain time. And based off when your V1 gets activated, when that letter flashes, then hopefully the EEG headset would pick that up, and your program or your BCI will recognize that means that they want that desired letter. Now, FEP would basically have 26 letters all flashing at a different frequency. Whichever letter the participant is staring at, their V1 will oscillate at a similar frequency that is getting flashed. And due to the frequency that you see in your recordings, you will know which letter that they're looking at. And then CVEP is basically a code. So it's kind of like frequency, except it might just be a different pattern instead. So every letter would have its own distinct pattern, and then you would try to pick up that pattern in the V1 with your recording. So all 3 of these work for different methods, and it really depends on which one best fits your solution or how many nodes or classifications you have to do on which these 3 you need. And yeah, and that was our presentation. It was a little shorter today since we didn't want to go way too in depth into neuroscience. We basically just want to give people a general overview and idea of how EEGs work. If you want to go more back into coding and Jupyter notebooks and that kind of deep end, we will have a ML workshop next week, and that one will be with live EEG data and Kaggle competitions, because right now it's really hard to get your own data. So Kaggle is the best way to learn how to mess with, clean, and make your own data. And if anyone has any questions, this is a perfect time. You can always ask us now or on our Discord or send us an email. And just once again, everything that we talked about here is pretty much what is thought as the main ways to use BCIs because they've shown the most results, but there's plenty of other things you can do with your recordings and also the waves that you read from different parts of your brain. We like to think, follow the guidelines of what your lobes are for, but once again, it's very hard to test that in real life. So there's a lot of uncertainty.
Yeah, just sort of to add on to that, like our brains are very complicated, and like the ones that we went over today are like the ones that are fairly certain that they happen because we know, okay, when you see something a certain way, flash a certain frequency, it's pretty cool that we know that our visual cortex would also respond in a similar way. But that's like a very specific brain signal that is fairly easy to start with, which is kind of why we're suggesting to start with that. But research in this area is definitely looking more into trying to understand brain signals in a more statistical sense and make sure enable us to extract information through using machine learning and other signal processing techniques to better be able to understand and decode like exactly what these little squiggly lines are made of, because our brain's always doing different things at different times. So trying to extract that is a pretty big research topic. So yeah, does anyone have any questions about like any of the brainwaves we went over today and any thoughts about them?
I guess we just did an amazing job, huh, Julie? Yeah, if you want, we'll probably stop the recording. If you want to ask us questions and not get recorded then, but I guess we're done then. Thank you everyone for coming. I hope that was informative and you now have a better idea of how you even get electrical signals from your brain in the first place and why we use the ones that we do.
Thank you.
Yeah, and like all this like neuroscience stuff, it's like pretty hard to get in the first time. don't feel like it's like a lot of information, because we always have different names for even the same parts inside the brain for some reason. So it's always going to be super confusing to like kind of work with the brain and try to learn the different names of it. But over time, you'll find that you'll figure out, oh, this is the frontal lobe.
Yeah, there's a giant lack of coherence in this field.
Yeah.